So in the last lesson, we spoke about forward reactions as well as reverse reactions. And we said that when the rate of the forward reaction is equals to the rate of the reverse reaction, we say that system or that reaction is in equilibrium. So these two rates are equal. But then a number of things can actually affect. Let me finish writing, otherwise I'll start writing something that I'm not supposed to. So okay, let me write. So this system is in equilibrium. That's what we said. And we've already shown, we drew a graph where here we have the forward reaction, and then after a while its rate decreases, and then after a while it reaches a constant rate. Then this one increases, after a while it reaches a constant rate. And where these rates are equal, we said it is in equilibrium. Right? Cool. So here imagine you had time, and here you had the rate of reaction. Okay, so it's very important for you to understand this so that you can understand everything that we're going to talk about in this lesson. Right. So a number of things can actually affect this equilibrium. There are a number of factors that can affect the forward reaction or even the reverse reaction, and those factors can be concentration. The other one is temperature, or what's the last one? Pressure. So this means that if we change the concentration maybe of the reactants, something will happen to this equilibrium. It will shift because there's now a change. If we maybe increase the concentration of the reactants, it will be disturbed. The system will no longer be in equilibrium, right? The same thing when we do the temperature as well as the pressure, right? And so how do we know what change is going to occur? Is it a matter of will the forward reaction be favored or the reverse reaction be favored? How do we know that? And to know that, we use something called the Chatelier's principle. So in essence, the Chatelier's principle actually helps us predict what effect a change in temperature or pressure or even concentration will have on the position of equilibrium in a chemical reaction, right? So this means that we have to actually define what is Le Chatelier's principle. So Le Chatelier says to us that if you apply an external stress, an external stress can be either you increase the concentration or you decrease it of either the reactants or the product. You can either increase the concentration, right? Either, or sometimes you increase the temperature and decrease it. Sometimes you increase the pressure or decrease it. That's what we mean when we say you are applying an external stress. When you apply this external stress to this system, that is, remember, in equilibrium, this equilibrium will change. How will it change? It will change in such a way that it wants to reduce the effect of the stress. So if we're increasing, it will try to reduce so that we can re-establish an equilibrium. So let me just draw another graph here. And this is a very simplistic explanation, right? And then here we have the rate of the reaction. So you had your forward reaction, reverse reaction. This is equilibrium. Let's say at some point you decide to increase the temperature. When you increase the temperature, something happens. So you find that you might have a spike, and then these things might try to again, and then you have a spike. This is the reverse reaction, and then after a while they will try to re-establish a new equilibrium. So this was our first equilibrium. This is our second equilibrium. Something happens. So because the system likes to always be at equilibrium, it likes to be balanced. If something happens, you apply maybe a stress, it will seek to kind of reduce the effect of that stress, so that again we are at an equilibrium, right? So this means that whatever change or stress you apply on a system, the system will seek to kind of counteract that change. So just shortly, we're going to talk about the effect of the concentration on equilibrium, the effect of temperature on equilibrium, as well as the effect of pressure on equilibrium, right? Cool. So where's my marker? Damn it, can't find it. Okay, so the first discussion, let's talk about the effect of concentration on equilibrium. So let us say we had a system that was in equilibrium, and then all of a sudden we increased the concentration of the reactants. Increased concentration of reactants. So we have a system, so we had A plus B, where the rate of the forward reaction was equals to the rate of the reverse reaction. So they were in equilibrium. So let us say when they're in equilibrium, this is the initial point, right? So you have your A here and your B. And you see that at this point it's balanced. So the system, we can say it is in equilibrium, right? Cool. And my voice is kind of trailing off there. I apologize. So the forward reaction is A plus B, which gives us C plus D, and the reverse reaction is C plus D, which gives us A and B. Cool. So when let's say we increase of the reactants, so increase the concentration of the reactants. This means that if we increase the concentration of the reactants, so we have A, B, another A, and B. So we have more A and B than C and D. The system wants to go back to equilibrium. So what do you think this system is going to do? So this system is going to say, now I want to, it will want to favor, now remember we increased the reactants, so the reactants went up. So it will seek to reduce the effect of this by simply favoring a reaction that uses up the reactants to produce products. Which reaction is that? That is the forward reaction. So it will favor the A plus B, C plus D, so that it can use up this sudden increase in product to form C and D, so that essentially this is forward. Essentially, the system can re-establish an equilibrium again. And then it does that. When it does that, it means we will form more product. So here we will form more C and D. And then as a result, finally, your system will be in equilibrium. You'll have C, D, C, D, and then you have A here, B, A, B. So now it's balanced. It's back to what is it? I'm trying to think. It's back to equilibrium. So equilibrium will shift in the direction that produces products, which is our forward reaction, right? Cool. So now let us say what we have is an increase in product concentration. So remember previously we increased the concentration of the reactants. Now we increase the concentration of the products. So initially your system, like before, it's at equilibrium. So you have your A and B here. I'm gonna be quick now because I've already explained most of this. C and D, right? If you increase the products, it means that your equilibrium will somewhat now be shifted. You'll have more products now, C, D, and your system will seek to kind of counteract that. So you have A. So now it was in equilibrium, it was balanced. Now it's a bit unbalanced. It's not in equilibrium, B, right? So what will happen? So we have an increase in the product concentration. So the system will want to counteract this, right? This means that the system will favor a reaction that uses products, that converts products back into reactants, and that is the reverse reaction, where um, where C plus D essentially goes back into A plus B, right? So meaning that it will favor this reaction, meaning more products will be formed so that the reaction can be balanced. And then finally, it will be balanced when after, so this is B, no, C, D, this is C, D, right? So now it's back um to equilibrium. So you see what happens. This means that the reverse reaction will be favored, like I mentioned. So this more products will be converted back into reactants, and then equilibrium will shift in the direction that produces more reactants. So now let us take a different case where we are decreasing the concentration of the reactants. So now let us say in this instant, we are decreasing the concentration of the reactants. So what happens? Initially we have A plus B and C that forms C and D, which are all in equilibrium. And now we want to decrease the products, the reactants, the concentration, we're decreasing it. So meaning there's no, maybe let's say we've decreased it, there's no more B. Now you see your system is no longer going to be in equilibrium. That equilibrium will be disturbed. D, so we have A over there. So what will happen in this instant? In this instant, your system will favor a reaction that produces more reactants. So they want to produce more reactants so that you can return back to equilibrium, so as to increase the concentration of the reactants. So meaning which reaction produces more reactants? The reaction that produces more reactant is the reverse reaction, where C plus D is converted back into A and B. So essentially, you have reached your equilibrium, where what is it? I'm trying to think. Some of your product would have been converted back into, let's say in this instant B, to make sure that your system is in equilibrium. So this means equilibrium will shift in the direction that produces reactants. Now let us do a case where we have a decrease in the concentration of products. Okay, so in this instant, we are decreasing the concentration of the product. So if we decrease them, maybe let us now remove D, meaning your equilibrium will be affected. In this instant, so this is A and B. In this instant, what will your system do? Your system will favor the reaction that produces more reactants so that the concentration of the products can be increased, right? So we decrease them, it seeks to increase them by favoring a reaction that produces product. And we know the reaction that produces products is the forward reaction, where A and B is converted back into C and D. So meaning a little bit of A and B will be used to produce D, C and D, right? And essentially our system is back to equilibrium. This means that equilibrium will shift in the direction that produces more products. Next up, we're going to focus on the effect of temperature on the equilibrium. So let us say now you have a reaction where A plus B reactants will produce C and D, and then also on the other hand, they write to you that the heat of reaction, or the enthalpy, we've spoken about this in the previous lesson, is 20 kilojoules, right? Cool. And then we said that if this is positive, it means that it is an endothermic reaction. It is a reaction that absorbs energy, meaning that the forward reaction is endothermic. I'm just going to write endo. It's endo. Okay, let me write it in full. Endothermic, right? So meaning that A plus B is your endothermic reaction. If the forward reaction is endothermic, it means that the reverse reaction is actually exothermic. If this value was negative 20 kilojoules, we would know that the forward reaction is actually exothermic and the reverse reaction is endothermic. So meaning that A, this is exothermic, right? Cool. So we've already spoken about what is an endothermic reaction. It uses up heat. And then how would you do that? Notice that a reaction that uses up heat, if you touch the surface of your container in which you're performing the experiment in, it would actually cool it down. If it was exothermic, it releases the heat. If you touch the container of the whatever in which your reaction was taking place in, you'd actually feel that the container has gotten somewhat warm. So now so maybe it was at 25 degrees centigrade, right? And then you decide to increase the temperature. You take it to maybe 60 degrees Celsius, right? What do you think will happen? So when you increase the temperature, you're basically heating up the system. And your system will favor a reaction that uses up the heat. So you increase the heat, right? And your system wants to counteract this change. This is a stress that you apply. It will favor the reaction that uses up the heat. And between which two reactions which one uses up the heat? The reaction that uses up the heat is the endothermic reaction, right? So remember, the endothermic reaction will use that heat up, and it will essentially cool down your system. This means that the forward reaction will be favored in this instant, right? So as a result, your equilibrium will shift in the direction that produces more product, such that at least more heat, this heat that is being provided, can be used up, and your whole system can sort of cool down, right? But now let us say, what happens if you decrease the temperature? So you decrease the temperature. You decrease it was 25, maybe you take it to 0 degrees, right? What do you think will happen? Your system will favor the reaction that produces more heat so that it can at least warm it up a little bit. So you decrease in the temperature. It doesn't want that. It wants to go back to its equilibrium. So it will favor a reaction that increases the heat, that warms up the system. And that reaction that does that is the exothermic reaction. And we already said that the exothermic reaction is the reverse reaction. This means that more products will be broken down into reactant, will be converted back into reactants, so that the system can essentially release heat. So you decrease, it seeks to increase the heat. You increase the heat, it seeks to decrease it, right? So this means that the reverse reaction will be, I've already mentioned, will be favored. Equilibrium will shift in the direction that converts product back into reactant, right? Now let us take the case of pressure. What happens if we increase the pressure? What happens if we decrease the pressure? Okay, so let us say you have your container there in which you are performing your experiment, and then you had A plus B that was in equilibrium, so it was reacting to form 2C plus D. So just kind of hanging on to our previous lesson, we can say that 1 mole of A reacted with 1 mole of B to form 2 mole of C plus. So let us say all of these are gases. Actually, it's important to mention this. All of them are gases, right? you'll see why this is important, and 1 mole of D. Right? Cool. So we can agree that we have 2 moles of reactant, 2 mole of reactant, let me write R, that produces 3 mole of product, 2 plus 1, 3 moles of product. So you have 2 moles of gas that produces 3 moles of that produces 3 moles. It's gonna become clear why I wrote that there. And now we have our system over here. Let me just do this. We have a system over here. We can either increase the pressure. Let us say we decrease the pressure. So decreasing the pressure is almost like increasing the size of your container. So you have your A, B. So you have your reactants in there, right? Cool. So when you decrease the pressure, your system will favor a reaction that increases the number of gas molecules. So remember what I said. I said you have 2 moles of gas molecules, which are our reactants, that produces 3 moles of gas molecules, which is our product. Which reaction? Remember, this is a reversible reaction. Don't know why I did this that way. This is a reversible reaction. So which reaction between the two produces more gas molecules? Obviously, it's the forward reaction, because for 2 moles, we get 3. So meaning your reaction will actually favor the forward reaction. The forward reaction is A plus B, which forms 2C plus D, right? It means that, so this means that more product will be formed. So we'll have a lot of C's and D's in here, right? Equilibrium will shift into will shift in the direction that produces more product. But now let us increase the pressure. The opposite occurs. If we increase this pressure, right, it's almost like we are decreasing. They look like they are the same size. So when you increase the pressure, it's as if you are decreasing the container. So your container is the size, it's decreased to that side. So now what happens? Your reaction will favor your system will favor the reaction that decreases the number of gas molecules, because the container is subsequently decreased, right? Here it had increased, so it will favor the reaction that increases the number of gas molecules. And that reaction that favors the decrease in the number of gas molecules is the reverse reaction, because for 3 we get 2 mole. For 3 we get 2 mole. So you're moving from a bigger number to a smaller number. So meaning more products will actually be formed than reactants. So this means that your equilibrium will shift to produce more reactants, right? I hope that makes sense, and in a way that I tried to explain Le Chatelier's principle to you, because this is how I try to explain it to myself, right? Cool. So this actually brings us to the end of this lesson.